quickly went over lecture 15. Basically, the whole point of chapter 6 is trying to make a connection between what our thermodynamic properties are to something that we actually care as chemists, right? That's the equilibrium constant, or how your equilibrium is built during your chemical reaction processes. So in our last lecture, we introduced the idea of ideal gas mixture. So instead of starting from the complicated reactions, let's just look at the oversimplified ideal gas reaction and mixture of ideal gases. So we start from our simple system. Some of the rules we derived from the ideal gas system will be further applied to other systems as well, like solutions or phase changes. Okay. So just to remind you a little bit, so lecture 12 is when we cover the basic of chemical potentials. That includes what's the definition of chemical potential and how do we derive that expression. So what we have here is the chemical potential of that species I at specific phase alpha. So that is a function of temperature at that phase alpha, pressure of that phase alpha, and number of moles of all other substances at that phase alpha. And that is by definition equals to the partial derivative of Gibbs free energy over the change of the number of mole of your substance I. And everything else was kept constant. So that's linked to the concept we went over, is say the chemical potential of a pure substance equals to the Gibbs free and the molar Gibbs free energy of that pure substances. So we're just looking at one single substance. So that's a link here. And in our last lecture, we first introduced the idea of ideal gas mixture, give it a more careful definition of what is an ideal gas mixture. So in this definition, wait, did we do that? Right, so we want to, so this part is the review. We were just talking about the chemical potential of a pure ideal gas. We make the link of your ideal gas, the potential of that pure substance equals to the molar Gibbs free energy. So this is a link we just met. And when we're talking about the ideal gas mixture, what do we have? Yeah, we defined that ideal gas mixture so that the partial pressure of that specific substance I is the partial pressure equals to its mole fraction times the total pressure of that entire mixture. And that's one of the definitions of ideal gas mixture. And using this definition, that at its equilibrium, the partial pressure of I satisfies Pi equals to chi I times P, we then move on to derive what is the expression of your chemical potential. So this is what we call the fundamental thermodynamic equation. So on the left, that's our chemical potential of your substance I at any given point in any mixture. And here, this is the mu I naught. So this one we're talking about the standard reference chemical potential or the standard molar Gibbs free energy of that substance I. So this is something you can find out by checking the thermodynamic table. And depending on what exactly is that mixture, you have this RT lowering partial pressure over P naught term to take care about what exactly is the amount of your ideal gas in that mixture. So this part should be a quick review about the chemical potential of an ideal gas mixture. So this is something we discussed last time. And we did an example problem together. So in this example problem, what we're saying is, let's say you have this fundamental equation, and you can check the table to find out what that, okay. You have this fundamental equation, and you have changes for the process. So some of the things will come to play. So in this case, when we're looking at the delta GM, so this standard one will cancel out because we're looking at the differences, right? So you can just calculate the delta GM or the molar Gibbs free energy change for this process by looking at chemical potential of your final minus initial state. And in this case, we're using that RT lowering P final over a P standard minus RT P initial over P standard. You can find that information here. And in this one, let's just read it again. We're talking about 3 mole of a pure gas that's isothermally decreased. Its pressure is isothermally decreased from 2 bar to 1 bar at 400 Kelvin. So this part, what I say is when we say a negative delta G, so this stands for negative. I know it confuses some people, so this one is negative. So when the delta G is a negative number, and what we can take home is, well, in this reaction, delta H equals to 0 because it's isothermal and ideal gas reaction, so we know delta H is 0. And this on the left-hand side, your delta G is a negative number. Your temperature is a positive number, so your delta S is a positive number. All right, or your entropy increases. And if you look at what we have here, by decreasing the pressure, your volume will increase and your ideal gas will have more room to go around and the entropy naturally increases. So one of the things that I tend to do is after every problem, we can set up the calculation, you can do the equations and derivations, but at the end, we want to link it to some specific chemical properties or chemical transformation that is taking place. And that's for the mixture or the phase change or state change of the ideal gas mixture. And then we moved on to talk about the ideal gas reaction equilibrium. So this part, I'm going to just revisit it a little bit in a slower pace because now we're actually moving on to talk about chemical reactions that we care about as chemists. So this part is a review. When we say a reaction is at equilibrium, typically, we draw that arrow here with a double-ended arrow. So this means we have reaction at equilibrium. Now, this is our general form of the reaction. This is our stoichiometric coefficient. And on the right-hand side, we know that at equilibrium, your delta G in this closed system equals to 0. So this entire thing adds up to be 0, right? So your chemical potential times the stoichiometric number adds up to be 0. Nothing fancy, just like write whatever you already know in the general equation form. And then we spend some time to define the standard equilibrium constant, Kp. So this whole process is we're using this hypothetical equation of AA plus BB goes to CC plus DD. So, or you can rewrite this equation into like 0 minus AA minus BB plus CC plus DD. It's the same idea as we've seen before. All right. Next up is we have our understanding on what is your chemical potential be for this reaction at equilibrium. So write out this expression of the summation of your stoichiometric number times chemical potential adds up to be 0. So that's what we have. Then we used that fundamental thermodynamic equation for ideal gas mixtures. So this is the equation we derived before. We basically add these two equations together. So plug in number for every of the terms in this equation using this expression here. And by doing that for every term in there, we end up having the expression as following. So by plugging the number here, what we have is each of my mu c equals to this mu c naught plus RT ln PC over P naught. And the same applies for every other ingredient in your pot. And then what we did is move all the chemical potential term to the left because we want an expression of chemical potential in some kind of relation with an experimentally measurable properties like partial pressure. So in this case, by moving it around, on the left, we have all the chemical potentials. And on the right, you have all the partial pressures. All right. And then we're using our thermodynamic understanding that your chemical potential equals to the molar Gibbs free energy of a pure substance. So we rewrite it, our left-hand side, using like chemical potential, and we rewrite it into the sum of your molar Gibbs free energy added up together. And what we have is when you have stoichiometric number times your molar Gibbs free energy, and the sum of that for a reaction gives you the delta G of that reaction. So left-hand side becomes the delta G naught of a reaction. And we went over examples in how to calculate delta G naught of a reaction under standard condition from the thermodynamic table. All right. And then on the right-hand side, we simplified our expression for our partial pressure. You have negative RT, and then you have your stoichiometric coefficient, small a, b, c, and d. You write it out. Now, when you put that small a, b, c, and d into the logarithm, they went on to the power, right? So that's the law of logarithm. So when you have like x ln a, it's effectively the same as ln a to the power of x, right? So this part is what we're doing here. We're just effectively rewrite everything here and put them all into the logarithm instead of the negative RT. And this whole thing, we then define it to be our standard equilibrium constant, or Kp. And by looking at this expression here, we have the relationship between your reaction, the Gibbs free energy of your reaction, so delta G naught equals to negative RT ln Kp. All right, so this part is just a derivation in how do we get here. And if you think about it, now this delta G naught is something you can calculate using your thermodynamic table. And by knowing what the delta G naught is, you have your equilibrium constant. And your equilibrium constant consists of your partial pressure of each of the ingredients. So what that means is as long as we know what our delta G of the reaction is, we have an idea about what the composition my reaction mixture will have at equilibrium. And we then take some steps to generalize our expression for the equilibrium constant and also for our Gibbs free energy of the reaction. So instead of having like AA plus BB equals to CC plus DD, we're just saying for any chemical reaction, one have this expression hold true. That is the delta G naught, or the Gibbs free energy of the reaction at the standard state equals to negative RT ln P. Or if you rewrite that relationship, it's your equilibrium constant Kp naught equals to the exponential of negative delta G naught over RT. So this part is they're just the same. It's just mathematical operations here. And the definition of our equilibrium constant, it's called Kp because it's defined using the partial pressure. Now it can have other forms of that equilibrium constant, and we will talk about that when we talk about like concentration in solution and so on. Now for now, what we have is this term here looks like a big pie. This one is just say it's a product, right? So this big pie, if you write it as like AI, it just basically tells you it's a product of A1 times A2 times A3, et cetera, et cetera. So your equilibrium constant equals to a product of your partial pressure over your standard pressure with the power of your stoichiometric coefficient, right? And in this case, if you think about the dimension of your equilibrium constant, it is always a dimensionless property because the pressure, your partial pressure, and the standard pressure P naught will always have the same unit, and their unit will cancel out. So your equilibrium constant is always a unitless property. It also fulfills our expectation in here, right? So your equilibrium constant, Kp, is within the logarithm. We do not expect it to have any unit. And the reason unit cancel out is within here, within its definition. Okay. With that in hand, we then have, this part is just rewrite everything we just derived. So you know how to calculate the delta G of a reaction from the thermodynamic table. And you have the relationship between your equilibrium constant and the delta G of the reaction. Now, everything till here is very generally true. We're not talking about only ideal gases. So these are just definition of your equilibrium constant, whatever system you're looking at. Now, for ideal gases, we have ways to further simplify it. So for example, your Kp naught for an ideal gas reaction, it's a function of temperature only. And we'll talk about that dependence of equilibrium constant at temperature next time. And this one is called the standard or pressure equilibrium constant. That P stands for pressure. And we have an example together. So let's work on this example together. So I think I can just do it on the board. It might be easier. Okay. Let's just read the question together. What we know is about 0.15 mole of oxygen gas is placed in an empty container which volume is known. And we say the equilibrium is established as 4,000 K. And we find out at equilibrium, the total pressure equals to 2.175 atm. Ask us to find the equilibrium constant and also the delta G of the reaction at 4,000 K. And we're assuming ideal gases. So we'll just write out some of the things we know. Fine. I have a very small one. Let's see if I can finish it. So what do we know? We have equilibrium reached at 4,000 K. So your P equilibrium that's given is 2.175 atm. And that also equals to 2.204 bar. So a few of the things we can derive is, first of all, we need to know, like, how is my reaction taking place at equilibrium? So because we're talking about ideal gas mixtures, so the first step we are doing it is we're using the PV equals to N total times RT, right? So your N total here at equilibrium equals to your pressure times volume times RT over RT. And in our question, we know the volume, we know the pressure, we know the temperature. We also have our gas constant. So we can plug in our number here. So that's 2.175 atm times the volume, 32.80 liter RT. So this one, I just choose it because we are talking about atm and liter. You can choose whatever gas constant you like. atm liter per mole per Kelvin times 4,000 Kelvin. So plug in the number to get about 0.2172. Let me find that larger chalk. Fine. And the second piece of information we want to know is like how much reaction is taking place. We know that initially we have 0.15 more of oxygen that's being placed in that reaction mixture. And this equilibrium before the oxygen is 1, and in front of that oxygen atom, that's 2. So what do we have here? So your number of more of oxygen initial equals to 0.1500 more. And given we know the reaction is O2 in equilibrium with 2 oxygen atom. So in here, the stoichiometric coefficient for O2 equals -1. And that stoichiometric coefficient for oxygen equals to 2. All right, so that's our initial number of more. So at equilibrium, what do we have? So the number of more of oxygen at equilibrium equals to the 0.1500 minus our extent of reaction. Right, so that's how much oxygen has been consumed. We don't know yet, but we can express it in the extent of reaction. And likewise, number of more of oxygen atom at equilibrium, that just gives me your 2C more. So your total at equilibrium will be the sum of these two numbers. And what we have is 0.1500 plus the extent of reaction. I'm not very good at writing the extent of reaction, so I'm just like randomly write it. Don't judge me by how I write my Greek letter. And more of reaction. And this total number of more of reaction, we can have that calculated here. So that's your total number of more of gases at equilibrium. And that equals to the 0.2172 more. So obviously, with this expression here, we can calculate what that extent of reaction is. So that gives you the C of the extent of reaction equals to 0.0672 more. All right. So with that in hand, now we're ready to do our subsequent calculation of your equilibrium constant and your delta G. So how do we set it up? Now we know our equilibrium constant is defined using the partial pressures of each of the reactant or product, right? So your Pi of oxygen equilibrium equals to the mole fraction of O2 at equilibrium times the total pressure at equilibrium. So there are lots of things we know. So your chi equals to the 0.15 minus C. You can also replace it with a number over the total number of moles C. So this one gives you your chi oxygen at equilibrium. And times your total pressure. And this one is known to be 2.204 bar. You can also use ATM. You can use ATM or bar, it doesn't matter. And you get some number there. And likewise, you do the same calculation for your oxygen atom at equilibrium. It's the oxygen atom at equilibrium times the P equilibrium. You do that calculation. And one of the nice sanity check is once you finish this calculation, just add these together and check if these addition equals to the total pressure. And that's a nice sanity check to make sure you didn't do any calculation wrong. And then we have our equilibrium constant equals to the product of all your species with partial pressure over P naught and with a power of stoichiometric coefficient. So this is why we're using the bar here for the total pressure. It's easier for you to cancel out that. And you can calculate your equilibrium constant and your delta G naught. That's equals to the negative RT ln Kp. And you have the results. All right. So this should be one of the easier questions to answer since the reaction is relatively easy. And when you have like more complicated reaction, you might need to solve a quadratic equation to solve for that extent of reaction C there. Okay, so that's the pressure version of your equilibrium constant. We also have other versions. For example, you can have the concentration equilibrium constant that will come to more play when we talk about solution phase equilibrium. And I think next week we'll finish the phase, which is chapter 7. And hopefully the week after, we'll start talking about solutions. So when we're talking about the concentration equilibrium constant, it's pretty much the same, just instead of having that partial pressure, we manually define that Pi equals to the concentration times RT. So here is your concentration, that is a mole per liter, more per liter. Right, so that's your number of mole divided by volume. So using your ideal gas law, you can have an idea about what is your concentration is as a function of pressure. And your Kc equilibrium constant thus becomes a product of your Ci over C naught and to the power of your stoichiometric coefficient. And your C naught is set to be 1 mole per liter. You can also express this in mole fraction, and it's pretty much the same idea. Use it to chi I. But nevertheless, there are different forms of equilibrium constants. Their nature is pretty much the same. We're just talking about what is that partial thermodynamic property over the standard one for any of the chemical species involved in their reaction. Okay. The next topic of today is the temperature dependence of equilibrium constant. So remember, we say that for ideal gases, your equilibrium constant is only dependent on temperature. And that expression is called the Van 't Hoff equation. And we'll do a derivation together and see how do we use it, use that derivation, and see how do we use the Van 't Hoff equation to solve actual problems. So we start from our original definition or original relationship we identify, right? So the delta G of your reaction equals to negative RT times the ln Kp. So in this case, what we do is let's just put the ln Kp on the left-hand side and everything else on the right-hand side, because we're trying to find the temperature dependence of equilibrium constant, right? So everything with equilibrium constant on the left, everything with temperature or everything else on the right. Now we're trying to find the temperature dependence of equilibrium constant, so we differential at both ends with T. So on the left-hand side, we have the change of ln K naught P over dt, and on the right-hand side, that is our d over dt negative 1 over RT times delta G naught. Right, so we're taking differential on both ends and then divide both ends with a dt. Next step is, again, using calculus. So we should be pretty familiar, right? When you have a product inside the differential that equals to x dy plus y dx. So by doing that, we can simplify our right-hand side The left-hand side stays the same. And the right-hand side becomes, now your x is your negative 1 over RT. Your y is your delta G. So what we have is negative 1 over RT d delta G naught over dt plus delta G naught of that 1 over RT squared. All right, so that's just calculus. Let's just write out what we can. And there are something else we know. So first of all, we know that delta G naught, or the Gibbs free energy of the reaction, equals to sum of every stoichiometric coefficient times your molar Gibbs free energy, and your dGm, that's the molar Gibbs free energy, equals to negative S dt plus VdP. So if we're focusing on this term here, the dG naught over dt term, what do we have? We're trying to find an expression for the dG naught over dt that equals to d over dt, and plugging this number to this delta G here. That's just a summation of your stoichiometric coefficient times the standard molar Gibbs free energy. Now, some of the things are not dependent on temperature, like your stoichiometric coefficient doesn't care what your temperature is. So we can write that out to be the summation of your stoichiometric number. And in there, we have the dG naught over dt. All right. And from our Gibbs equation, so again, when we're using our Gibbs equation, when you end up having something like this with the relationship of your, for example, this one, the nature of it is the temperature dependence of your Gibbs free energy. So when we're talking about the dependence of certain intensive properties like temperature or pressure of a state function, check the Gibbs equation to find out what that is. So in this case, when we're looking at this relationship, in the Gibbs equation, we have the partial derivative of dg over t at constant p equals to negative Sm, right? So we're talking about the standard pressure scenario. So our pressure is by default, that's at constant pressure. So what that tells us is this term just become negative, just become the S naught, or the molar entropy of your species of interest. So this entire summation thus becomes the negative S standard molar entropy of that species I. All right. And in this summation, what do we have? We have your stoichiometric number. You have your entropy of each of your reactant or substrate. So this summation effectively just gives us negative delta S, or the standard entropy change of a reaction. All right. Again, this is why we need to go over that equilibrium relationships so that these things will make sense to you when we're applying them. So this is the first term we went over. And with this in hand, this term here, then the expression of your temperature dependence of equilibrium constant then becomes something we can write out. So this one is a negative 1 over RT times the negative entropy change of the reaction plus delta G naught over 1 times 1 over RT squared. If I put the 1 over RT squared at the front, and simplify it. So this is one of the technique. You can simplify it and just look at whatever on the bottom and just take that to the front, and then everything else you write it out. This becomes delta G naught plus T delta S naught. So these negative cancel out. You need one more temperature here, so we have a temperature in front of your delta S naught. This becomes very familiar. Remember our definition of delta G naught equals to delta H naught minus T delta S naught. Or effectively, what we have is this expression becomes the temperature dependence of your equilibrium constant, thus becomes the delta H naught over RT squared. All right. So in order to use this expression, and this is what we call the Van Hoff equation. How are we doing here? Really? Okay, sounds good. So with this in hand, what we want is we want a way to actually plot this relationship so we can find out what our delta H is. So now remember the whole point of having that equilibrium constant, and now by monitoring how the reaction goes, you build a link between how your reaction equilibrium mixture looks like with some thermodynamic state functions. Right, there are something you can measure, there are something you do not have measure. So it goes both ways. So for example, if you have the thermodynamic table, you know what delta G, delta H is, you can derive what equilibrium mixture looks like. Or you can determine delta H of a reaction by measuring the equilibrium component at different temperature and plot it to find the delta H. All right, so the way we do it is further simplify this equation. So we have the differential of like 1 over T equals to negative T squared dt. That's just calculus. So what that means is instead of having our dt here, you can rewrite it to be the d ln kp over d 1 over t. So this term here. And you can cancel out the t squared. So how does that happen? So what do we have? It's your dt equals to d 1 over t over negative t squared. So yeah, let me not skip any step to make sure you're following me correct. So d ln kp over dt equals to d ln kp over d 1 over t over minus t squared. So that's this term here. And on the right-hand side, you have the delta H naught over RT squared. Now, this term, if you move it on the right-hand side, you cancel out that t squared on the bottom. So we end up having a expression of d ln kp over d 1 over t equals to negative delta H naught over R. All right, so this part is again just using calculus. What does that mean? We did all these derivation to this expression. So this means we have an experimental way to measure what is the delta H of that reaction if we know the equilibrium constant at different temperature, right? So if we plot the ln Kp, so in this case, if we plot the ln Kp over 1 over T, so this is on the y-axis, that's your ln Kp. On the x-axis, that's your 1 over T, or T minus 1. The dashed line just tells you what these T minus 1 is corresponding to if we're only looking at temperature. And by looking at this plot, you have a way to calculate the delta H of the reaction. And you can compare that calculation with your thermodynamic table and find out which one is correct. And chances are you might be asked to do it in both ways and compare it at a later time. So this is one of the example problem together. So it says use this figure to estimate the delta H naught for this reaction in the range of 300K to 500K. Now this one is just a straight line. And what we know is the slope of this curve is the negative delta G naught over R. So what you want to do is find 2 points of interest. It doesn't matter which point you have, it's just calculating slope. I just randomly pick 2 points. One is here, because we know it, the law in Kp equals to 0. It's easier to calculate. And you estimate what that temperature is. So that T minus 1 is about 0.0022 K over 1. And you can also have a random point like P2. So I'm picking something like here, where we know what that X and Y axis are. So at point 2, your ln Kp equals to 20, and your T minus 1 is about 0.0040 K minus 1. Then calculating the slope equals to, on the y-axis, so 20 minus 0, and x-axis 0.0040 minus 0.0022. That's about 1.11 times 10 to the 4. Right. And note the slope. Do you have a unit? Because on the top, your ln Kp doesn't have any unit. On the x-axis, it has a unit of K minus 1. So the slope will have a dimension or the unit of K. And obviously, you can calculate delta H naught equals to negative R times the slope. And you plug in numbers and et cetera, et cetera. So in your PChem lab, this will likely to be one of the experiments you did, right? So measure the equilibrium constant at different temperature and plot it using those data points and actually find out the slope. And then use that slope to find the delta H of the reaction. All right. Do we have any questions? We only have 5 minutes left. I don't want to go to our next lecture, but any questions? No? Yes.
Can you go up to the previous page? Yeah, and I think for like the 1 over t, it should be equal to negative 1 over t squared.
Which one is it?
Like the one with the
You want to just come here and point out? Yeah? It might be easier. Our class is finally small enough so we can do this.
It's like this part.
Uh-huh.
So shouldn't it be like 1 over t squared? Because if it's negative.
Oh yeah, it should be negative.
Yeah.
Sorry. Yeah. It should be like this one. Like that. Yeah. My bad. Sorry. Okay. All right, if that's everything, I guess we'll conclude for today. Happy Thanksgiving. We won't post your grade until next Monday, so